Hi everyone, in this little video I'll be telling you about negative transcriptional regulation. So negative transcriptional regulation involves a protein called the repressor. The repressor protein attaches to the DNA at the operator. So the operator is a regulatory element of the DNA that is downstream of or after the promoter. So the way that this negative regulation works is when the repressor is attached, the RNA polymerase either cannot bind to the promoter or can bind but is physically blocked and prevented from transcribing. So when the repressor is attached to the operator, we do not get any transcription. Okay? So there are two types of genes that we've talked about, inducible genes and repressible genes. So the first type is inducible genes. So inducible genes are genes that encode catabolic enzymes. So we are not going to need to make these genes normally. We only need to express these genes and make these enzymes when we encounter the specific nutrient that we need to catabolize. Consequently, if we have an inducible gene that's under negative transcriptional regulation, the default is going to be for the repressor to be on the operator. Because most of the time, we're not going to need to be making this transcript until we encounter the nutrient. When we do encounter the nutrient, then we're going to have either the nutrient or a metabolite of the nutrient come into the cytoplasm, and it's going to function as the inducer. So the inducer is an effector molecule. It's going to bind to the repressor and change the shape of the repressor. Okay? So the inducer binds to the repressor, the shape of the repressor changes. This new repressor shape does not bind so well to the DNA. So the repressor comes off into the cytoplasm. Now, the sigma factor and RNA polymerase can easily bind to the promoter and then move their way down the DNA and transcription will happen. So when we have the nutrient present, then the nutrient or a metabolite of the nutrient will act as the inducer, causing the repressor to be removed from the operator and allowing transcription of the inducible gene. Get my DNA back together here. All right, the second type of gene is the repressible gene. So repressible genes encode anabolic enzymes. So these enzymes are typically going to be made. These genes will normally be expressed until the amount of these enzymes has been stockpiled to such an extent that we have plenty of the enzyme product and we no longer need to transcribe this gene. But normally, if we have a repressible gene that's regulated by negative transcriptional regulation, we're going to start out with the repressor in the cytoplasm, such that the RNA polymerase / sigma factor and RNA polymerase will be able to bind to the promoter and transcribe the gene, and then we'll be able to translate that transcript into the enzyme and then make whatever product we need. When we have enough of this product, then the product or some, again, related compound is going to come in and act as the co-repressor. So the co-repressor is going to find the weirdly shaped and inactive repressor in the cytoplasm and bind to it. The co-repressor is also an effector molecule. So when the co-repressor binds to the repressor, the shape of the repressor is going to change into a shape that can now bind to the DNA. So when we have plenty of this anabolic product, that product or a related metabolite of that product is going to come in and serve as the co-repressor. Now, even if the RNA polymerase can bind, so RNA polymerase binding is going to be decreased, But even if the RNA polymerase can bind, it can't transcribe. So negative transcriptional regulation involves the binding of a repressor to the operator sequence in the DNA, and when the repressor is on the operator sequence, RNA polymerase binding is decreased, and RNA polymerase, if it can bind, is prevented from transcription.